So thank you very much for coming to the special class. I had missed a couple and we are getting a bit slow, so it will be good to get to speed. And we will be meeting tomorrow also in class. So what do we want to do today? I don't think I will take 1.5 hours. We will see how far we go. It's late in the evening. So we want to continue our study of non-interacting ideal systems. And we want to see what kind of rich physics can we derive through these studies. And you will see, even though non-interacting and ideal sounds so boring, you can get a lot out of it. So last time we talked about occupation numbers. We very briefly talked about fermions. We talked about bosons. And the whole idea was that in fermions, the occupation number in any level can be only 0 or 1. In bosons, the occupation number can be 0, 1, 2, all the way up to infinity. So today, and if this confuses you, don't worry, we will get to fermions and bosons in Thursday's class. But it's good to know what they are. And what we are doing today is to study a particular type of bosons, which are known as phonons. So what are phonons? Phonons capture how does a crystal vibrate. It captures the possible state of vibrations in a crystal. So let's see what it means. So again, if fermions, bosons confuse you, that's totally okay. We really haven't done them. I've just given you flavor of what's going to happen. And phonons also, phonon is one of the most, we all have a feeling that we understand what is an electron, what is a proton, what is a neutron. Phonon is a bit complicated, and hopefully in today's class and tomorrow's class, it will become clear as to what it is. So let's get started. So our picture is something very basic that we want to explain. So in early 1900s or late 1890s or whatever, people knew by that time that if you measured the heat capacity of a certain material, let's say the heat capacity at constant volume versus temperature, it behaves like this. It goes to 0 as the temperature becomes very small, and then it becomes constant at higher temperature. And this constant is 3nk, the number of atoms in this system multiplied by some number. Of course, back then there was no Boltzmann constant. They had a gas constant, right? So you could express this thing in units of 3R, for example, if you have intensive heat capacity or something like that, right? So, but the main point remains that as temperature goes to infinity, heat capacity becomes constant. As temperature goes to 0, heat capacity goes to 0. And this observation, even though they had it, it was very hard to explain as to why it would happen. Using classical mechanics, they were unable to explain it. So classical mechanics could not explain above. In order to explain this, we really needed quantum statistical mechanics. Both of the things were needed at the same time. Without quantum statistical mechanics, this could not be explained. So that's what we are going to do in the next 2 classes or so. But first, I have to explain to you as to what goes wrong in the classical mechanical treatment. Why I will show to you as to how does indeed classical mechanics. So in classical mechanics, I will show you next that the picture is that the heat capacity is constant. So if you assume a classical mechanical model, the heat capacity just does not change. Why do you have a person behind you, Alex?
Because it's Kinjal.
One moment. Why cannot hear you? Sorry. Yeah, say again.
Because it's Kinjal.
Why is Kinjal behind you? Anyway, I don't want to know. So, okay. So let's look at the classical mechanical treatment. What does it mean? So we will start with the classical mechanical treatment, and you have done something like this in the bonus problem in the second homework and also in the midterm. That's what you did. That's the treatment we are going to repeat here. So classical mechanics says the simplest classical mechanics treatment is to assume that a chemical or a material is made up of n independent atoms, and each atom is oscillating around some equilibrium position. Around some equilibrium position. The equilibrium position could be a result of being the atoms being located in the corners of a crystal, or the equilibrium position could be due to them having formed some bond, but there is some equilibrium position and they are oscillating around it. And we will assume that the oscillations are small. So if I had to write down the potential energy of this system as a function, so the U potential energy as a function of R, where R is R1x, R2x, R3x, going on to Rnx, one moment. What I mean to say is R is a 3n dimensional vector. So for first atom, we have R1x, R1y, R1z, and it goes on to Rnx, Rny, Rnz. Okay, so it's a 3n dimensional vector. So if the atoms are oscillating around their equilibrium, this is going to be some equilibrium energy of the chemical compound or of the crystal, whatever that number is, some constant, plus partial U by partial R, and I'm writing partial in a sloppy manner. It could be total derivative multiplied by R, because it will become clear in a moment. I'm just going to think about some radial distances. So there could be some angles also, plus double derivative multiplied by R square. However, we are talking about close to equilibrium. What happens to the force close to equilibrium? Force close to equilibrium is zero, right?
Professor Tiwari?
Yeah.
Yeah, the screen is really grainy. I mean, the resolution, I don't know if that's just for me or is it a common problem for everyone?
How grainy is it?
It's okay, but like if it's too small, I think it's difficult to read. Like if it's, yeah, that's anything.
Yeah,
Okay.
small lower indices are kind of hard to understand.
Okay, I will write big letters, okay? I don't think this is, yeah, sorry about that. I don't know how exactly to change this, so I won't experiment too much. Let me just write in big letters. So the point being that if you're close to equilibrium, this first derivative is zero. Okay. And why is it zero? Because that's the force, right? So let's call it equation number 1. So what are we saying? We are saying that close to equilibrium, U of R is equal to U naught plus the term corresponding to R is 0. So we are left with double derivative multiplied by R square plus higher order terms, but we are going to ignore these because R is small. So what do we mean by R here? So we have an atom, some atom, and we are talking about how much has the atom has been moved to some other location. So if this was the equilibrium position, the atom has been displaced by some small amount R. That's what we are talking about, okay? So if R is small, the energy of the displaced atom can be written as U naught plus double derivative with respect to R square multiplied by R square. The first order term goes to 0 because the forces are 0 close to equilibrium, and the higher order term, third order and fourth order terms don't matter because R is small. Okay, in other words, U of R is approximately U naught plus, I'm actually missing something here. What did I miss over here? Anyone remembers? It's a Taylor expansion, right? So I should have a 2 over here. So this will be, let's call it alpha, where alpha is double derivative of this thing close to equilibrium.
I'm sorry, Professor Tiwari, why don't we have the first derivative?
Because you are at equilibrium. What happened? Let me draw the picture here. So you're talking about if this is U and this is R, close to equilibrium, it's going to look something like this. You have a harmonic approximation, or you have some curve. The point being that everything looks harmonic close to equilibrium. What happens to partial U by partial R here at the origin?
It's 0.
That's why.
Mhm.
So we are talking about small oscillations, okay? And furthermore, if you look at equation 2, are the oscillations symmetric? Is minus R or plus R any different from each other? No, right? The penalty in the energy is the same. So this is an example of a classical harmonic crystal. So it's classical. We don't have any quantum effects yet. And things are oscillating about there, or you could just call it classical harmonic oscillator. You don't even have to think about a crystal or a non-crystal. It's a classical harmonic oscillator. Things are moving around there, equilibrium position to the left and to the right. So what I'm going to show you that if this is for one atom, right? Now you could think about a system made up of n such atoms, and we are going to assume that every such atom, for the sake of simplicity, I will draw a crystal. We are going to assume that every atom is undergoing oscillations around its equilibrium position in a sphere of radius r, right? This one also, and they are doing it independently of each other. That's the independent approximation here. So what I'm going to show next is that such a classical harmonic crystal is going to have CV is equal to constant. Its heat capacity will not depend on temperature. In fact, it will come out to be the same as the heat capacity of an ideal gas. That's what we are going to see. Classical harmonic crystals are all very interesting for a variety of reasons. So if I'm going to be on any of your PhD qualifying exams, here is a question I'm quite likely to ask you. What is the thermal expansion coefficient of this harmonic oscillator? In other words, when you pump a certain amount of energy into the system, so how do we define thermal expansion coefficient? Thermal expansion coefficient is defined as alpha 1 by L partial L by partial T, or 1 by V partial V by partial T, right? Something like that. There can be a difference of 1 by 3 or something like that. So does anyone see, just by the picture that I drew without doing any math, what will be the value of thermal expansion coefficient for this crystal? You can unmute and answer. No one sees it?
Intuitively, I'd guess 0, but
Why?
does it have to do with the fact that the derivative of u is at
But even,
the
yeah,
first
you're
derivative
correct.
is
It will be zero. It will be zero. Why? Because a positive displacement is as likely as a negative displacement, right? It's like a pendulum. If you're sitting in a simple harmonic pendulum, your average location. So let's say you are sitting in a swing, Vedant, and I'm swinging you. And I pump in a lot of energy. I pump more energy, you swing higher and higher. What is your average location though? It's going to be the middle of the swing, right? So thermal expansion coefficient captures how does the average R change with temperature, and that thing stays zero. So for this system, average R will be zero, and you can see how it comes. You can even look at the math here. If you want to look at it mathematically, when you calculate the Boltzmann factor, this is an even function, right? E to the, so this is something you should DIY, do it yourself, try to work through the idea mathematically as to why is the thermal expansion coefficient for this equal to zero. So a harmonic crystal, if nature was made out of only harmonic springs, nothing would expand as a function of time. Things would oscillate more. It would look like they are expanding, but they would contract as much as they are expanding. And the average would be 0. I'm not going to prove this one today in math, in class. I'm going to focus on this one. I will calculate CV as a function of temperature and show you how that is actually constant. And the similar proof applies to proving the thermal expansion. So let's work on this. I'm sorry that the writing is a bit grainy. I really don't figure it out. If it becomes too bad, then please interrupt me and I will take a 5-minute break and try to solve it. So we wrote down that U of R is equal to U naught plus alpha by 2 R square. Okay, but that's not the only part. That's only the potential energy, right? So let's call it equation number 2. We called it equation number 2. We also have to think about the kinetic energy. So the total energy of this system is going to be U of R plus K, the kinetic energy, which depends only on the momentum, right? Kinetic energy does not depend on the position. Kinetic energy is only a function of how much momentum you have. So this is going to be U naught plus alpha by 2. And now we will switch to a Cartesian coordinate system. R square can be written as X square plus Y square plus Z square plus kinetic energy. What is that? 1 by 2m px square plus py square plus pz square. This is only for one atom. But what is the advantage here? We can write down similar terms for every other atom, right? Other atoms will also have the same energy. The variables will be the same. It's just that they are different atoms. So the energy, so if this is for atom 1, also for atom 2 is the same idea. The only thing is for atom 1, you have to consider x1, y1, z1. For atom 2, you have to consider x2, y2, z2, and so on and so forth. But the physics remains the same. The form of the energy is going to be the same. So our approach here is going to be that to calculate the n particle partition function Qn, we will just calculate Q1, the one particle partition function, and raise it to the power n. Okay, that's going to be our idea. So we call this as equation 3, the total energy of the system, and we call this as equation 4. Why can we do this? Because our atoms are independent. Okay.
But they are indistinguishable, right?
Yeah, we will take care of that.
Okay.
So, okay, let me take a step back. We are talking about a classical system, so we won't worry about indistinguishability. So in my classical world, Vedant is different from Alex, is different from Patrick, is different from Suiman. Okay? We will talk about indistinguishability a lot after spring break. For now, I'm talking about classical systems, so no need to consider indistinguishable. They are classical. So I have to write down Q1, classical. How do I do that? What is the definition of Q1? Q1 is going to microstate and calculating e to the power minus beta E nu, right? That is the definition of the partition function. Here, how do I do that? Here, it becomes an integral, right? Because every particle can move in X, Y, Z space. It can also move in Px, Py, Pz space. So we did such an integral earlier in the class, and you have done it in your homeworks also. So that's the integral we are going to use here. So we are going to do for every single particle an integral over P coordinates. So Px, Py, Pz, triple integral, and an integral over R coordinates, Rx, Ry, Rz. And the integral is going to be of exp minus E of P comma R divided by KT. And here we will have D3P and D3R. So I can do my first quantum mechanics fudge factor. The second factor will be the n factorial fudge factor, which will come later. So as I mentioned, I'm not worried about indistinguishability at this board. In fact, in your midterms, there will be no points deducted whether you got something correct or wrong due to indistinguishability. Don't worry about that. Here, I want to introduce a bit of quantum mechanics and take into account that quantum mechanics says that in phase space, the resolution that you have is limited by Planck's constant h, right? So when I count the number of microstates, I have to divide it by 2 pi h cut whole cube. Because this is, and this takes into account of P and R together. 2 pi h cut is just h, okay? So I'm dividing by 2 pi h cut whole cube, and this is my Q1. Let's call this equation number 5. So on the next page, we are going to calculate this equation, this integral. In order to calculate it, what do we need? We need to put E of P comma R over here. Where are we going to get E of P comma R here? We calculated it in equation 4. Equation 3, E of P comma R is written for us, right? So we will take equation 3 and put it in equation 5.
I have a quick question. Sorry.
Uh-huh.
When we derived the microcanonical ensemble, we explicitly considered this factor of in the phase space. But in the canonical ensemble, we didn't really look at that. Now we're using a canonical partition function, but we're intentionally introducing this phase
You
space.
can always look at if you're counting microstate space, if you're counting, it's not a function of microcanonical or canonical. If you're counting microstate in phase space, you have to divide by 2 pi h cut whole cube. But nothing to worry about because we are not interested in Q. We are interested in log of Q. It will just go away.
Okay.
We rarely care about the magnitude of Q. We basically care about log of Q, and furthermore, we differentiate it with things. So it's not an issue. So put equation 3 in equation 5. Yeah, so this 2 pi h cut whole cube, anytime you are thinking in this space, the PR space, you have to worry about 2 pi h cut whole cube. It doesn't matter whether it's microcanonical or canonical or grand canonical. So when we do that, we get Q1 is equal to e to the power minus u naught by kt. The first part of the energy just comes out, divided by 2 pi h cut whole cube, and a 6-dimensional integral over px, py, pz, x, y, and z. And here we are going to have e to the power minus beta alpha x square by 2, e to the power minus beta alpha y square by 2, e to the power minus beta alpha z square by 2, e to the power minus beta alpha px square by 2, e to the power minus beta alpha py square by 2, e to the power minus beta alpha pz square by 2, multiplied by dpx, dpy, dpz, multiplied by dx, dy, dz. Okay, how did I get here? Just look at this form. E is u naught plus alpha x square by 2 plus alpha y square by 2 plus alpha z square by 2. Similarly, px square by 2m, py square by 2m, pz square by 2m. So I missed something here. All of this should also have an m. The p term should also have an m. Okay. What can I do next? Well, I can realize that this is actually a product of one-dimensional integrals. It's not really a 6-dimensional integral. The beauty of exponential in classical mechanics is that everything is a product of each other. You can just remove it. So what does this come out to be? This comes out to be e to the power minus u naught by kt 2 pi h cut whole cube integral of px e to the power.
Would you have the alpha for the momentum terms? You wouldn't, right? It's only for the position terms.
Oh, yeah. Good call. Okay. That's how it is. So I have a m for the momentum term and alpha for the position term. So this is going to be e to the power. When I'm doing the momentum part, it's going to be e to the power minus px square by 2mkt dpx. There will be a similar integral for py, right? Where instead of px, I'm going to write py. Instead of py, I'm going to write pz. This term will become py or pz, something like that. The question now is, what is the range of px? When I do this integral, what is the minimum value momentum can take? What is momentum? Momentum is mass multiplied by velocity. Can the velocity be negative? Of course, right? It's not speed, it's velocity. So px can go from minus infinity to plus infinity. Same for py, same for pz. So instead of writing three separate integrals, what I'm going to have is a product of the same integral three times, right? Because the integral over px, py, and pz are the same. The only thing that you're doing is to change the name of the variable. Same thing applies to the integral over position. I will have x, which can also go from minus infinity to plus infinity. You can stretch the thing towards x direction in plus infinite. You can stretch the thing towards x direction in minus infinite. So it goes from minus infinity to plus infinity. And this thing will now look like e to the power minus beta alpha x square. Or actually, instead of beta, I'm going to write alpha x square by 2 kt. And now we have a dx. And same thing, instead of writing dy and dz separately, I will have a cube of this integral. Okay, so we have reduced it to two simple integrals. And this integral is actually one of the easiest integrals to calculate. Anyone knows the name of this integral?
Gaussian integral?
It's the Gaussian integral, and there is no real difference between the momentum integral and the position integral. They are basically the same, except that the prefactor that you have over here in the numerator is different. So how does the Gaussian integral work? We will use 1 by root 2 pi sigma square e to the power minus x square by 2 sigma square dx. If you go from minus infinity to infinity, this is equal to 1. That's the definition of a Gaussian integral. So it's the value of sigma that is changing for both of these, right? But otherwise, it's the same Gaussian integral. So this is equation 6. Sorry, this is equation 7. And this is equation 6. So if you use 7 and 6, if you use the value of the Gaussian integral in 6, what you get in one line of algebra is that Q1 becomes e to the power minus u naught by kt by 2 pi h cut whole cube. And by the way, this part I am following Chandler quite closely, all the heat capacity part. I will tell you when Chandler gives most of it as a homework. When I get to that homework problem, I will tell you, and that's what we will work through in detail. And the first integral is just going to be square root of mkt to the power 3. It's why did the square root of mkt come? That's the square root of 2 pi sigma square that you have for a Gaussian, multiplied by kt by alpha, square root of kt by alpha to the power 3. That's it. This is the integral. And now we can do the actual math and calculate it. This itself is going to be, what I'm going to do is to take out all the terms that do not depend on temperature and keep it in one side. So we have 1 by 2 pi h cut whole cube. That's the first term that does not depend on temperature. Then we have mk to the power 3 by 2. And then we have k by alpha to the power 3 by 2. And what do we have for temperature? We have e to the power minus u naught by kt multiplied by t to the power 3 by 2 coming from this one and t to the power 3 by 2 coming from this one. So we are left with t cube. And I will call all of this as G, some constant G multiplied by KT to the power cube. So, right, you can see here, this is K to the power 3/2. This is also K to the power 3/2. So we are left with K to the power 3. So KT whole cube multiplied by e to the power minus U naught by KT. Okay, where G is T independent constant. Okay, it's G includes the value of Planck's constant and things like that. We are not going to care about it too much. Let's call it equation 8. I will write down equation 8 again on next page. So we got Q1 is equal to G KT to the power whole cube multiplied by e to the power minus U naught by KT. And that's equation 8. I want to calculate the heat capacity of the whole crystal. For that, I need to look at Qn, the partition function for the n atom system. But I assumed all oscillators are independent. So Qn is going to be Q1 to the power n. If I take power n of this one, what will I get? I will get G to the power n, KT to the power 3n, e to the power minus nu naught by KT. That's equation number 9. So now I have my n particle canonical partition function. What I want to calculate is the heat capacity. How should I proceed next? Any ideas? How do I go from partition function to heat capacity?
Logarithm that?
Huh?
Apply log?
Okay,
Natural.
apply log. Good call. So if I apply log of Qn, what will that give me? What is this thing?
Helmholtz free energy.
Helmholtz free energy, right? That's one step. How do I go from Helmholtz to heat capacity?
Differentiated?
Will that directly give you heat capacity? It's a bit trickier. Heat capacity is P partial S by partial T at constant V. And S is minus partial A by partial T at constant V and N, right? So now we see a way. We have to calculate A. Once we calculate A using this formula, we put that into the formula, differentiate A with respect to temperature to get S, and differentiate it one more time to get CV. That's the step. So we'll start with A, then we will go to, so equation 11, and then we will go to equation 12. So first equation 10. What is A? A is minus KT, and by log, I mean natural log. It's a constant. Yeah, it doesn't matter in StatMech that much because we differentiate everything. So that's going to be natural log of G to the power n, KT to the power 3n, e to the power minus nu naught by KT. What is that? That's going to be minus nkt log G minus 3 nkt log KT. Right? So this one gives us minus nkt log G. This one gives us minus 3 nkt log KT. And the last one, it's log of exponential. So that becomes minus KT multiplied by minus nu naught by KT. So in equation 11, we have to differentiate this thing with respect to temperature. This term does not depend on temperature, right? KT and KT cancel out. So when we differentiate this with respect to temperature, what do we want? We want S is equal to minus partial A by partial T at constant volume. So this term, what is the partial derivative with respect to temperature? That is minus NK log G. The second term, we will have to do product rule, right? And not minus because we took a minus sign already. So this becomes a plus. For the second term, it will be plus 3n kt 1 by kt plus 3nk log kt, right? So what does this become? This becomes nk log of G plus 3n plus 3nk log kt. Okay, almost there. We need to, in order to get heat capacity, we have to multiply. We have to differentiate this with respect to temperature and then multiply by temperature, right? So we need T partial S by partial T at constant V. So this one does not depend on temperature, it's gone. This one does not depend on temperature. Only this third term depends on temperature. And what is that? That is going to be, so we have this T hanging outside and we differentiate it with respect to temperature. What do we get? 3nk divided by kt. So what do we get? T cancels out. Oh no, why is my other k also canceling out? Disaster. Oh yeah, because of the product rule. This thing itself is 3nk log k. Oh, you have to be careful with calculus. Plus 3nk log t, right? So we are not differentiating the first one. We are differentiating this term over here, right? So tt cancels out and we are left with 3nk. So we just showed that the heat capacity for a classical harmonic crystal is independent of temperature. It is extensive, it depends on n, and it is 3 multiplied by the Boltzmann constant. So physically, what is this telling us? It is telling us that the system, the harmonic oscillator, has 3n modes. Let me write it down on the next page. So the result that you just got is basically a clear sign of equipartition theorem. You have CV is equal to 3n multiplied by k. So you have 3n independent classical oscillators, and each oscillator contributes Boltzmann constant to the heat capacity. So the total thing is 3n multiplied by k. So we just showed that classical mechanics, at least classical harmonic oscillator CHO, could not explain CV versus T. So at this point, you might say, well, that's because you assumed a terrible harmonic oscillator. Maybe if you assume non-harmonic interactions, if your potential curve, instead of looking like a nice parabola like this, maybe if your potential curve looked like something complicated, you know, something like this, maybe that would solve my problem and I would get, you know, something nice behavior. Well, this is something that I mentioned in the very first class of 687, that in fact, no classical treatment can explain why CV goes to 0 as T goes to 0. And this is a simple yet profound fact. So anytime the temperature goes to 0 in classical mechanics, so like I said, so in order to derive all of this, we assumed a simple harmonic curve, right? And what I'm saying is, well, maybe we don't have that. Maybe we have something super complicated, you know, that looks something like this, some complicated potential energy function like this. Okay, this harmonic crystal where you have U versus R like this will give you a constant heat capacity. This n-harmonic crystal will not give you a constant heat capacity. The heat capacity will depend on temperature. But as the temperature goes to 0, it will still give you heat capacity finite. Why? Because in order to understand this, You have to zoom in more and more than my resolution. If you really zoom in over here, irrespective of whatever curve you have, very locally here, first of all, you still have harmonic behavior, right? As you get very, very close to equilibrium, you still have harmonic behavior. And secondly, arbitrary small excitations are possible. What do I mean by that? In a classical crystal, if the world was purely classical and you gave the system some very, 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 very tiny amount of energy, something like 10 to the power minus 200 joule, which is so small, the crystal will still be able to take that energy and move a little bit more because it's continuous, right? At any resolution, the curve is there, it exists. But that's not true. The world is actually quantum mechanical. There is an energy scale that applies. Quantum mechanics tells us that true nature of reality for small systems is not a uniform curve like this, but it's actually discrete eigenvalues. So the quantum mechanical picture says that you have these eigenvalues where we call this as the n is equal to 0 eigenstate, which still has a ground state energy, and we will talk about that. And then in this quantum mechanical picture, you could exist here, you could exist here, you could exist here, right? You could take arbitrarily small excitations in energy and you will be fine. Quantum mechanics tells us that there is a finite amount of excitation that you must have, which is equal to h cut omega. To go to the next level, you must be excited by h cut omega, right? That is the gap between these two levels. What does that mean? That means that if your thermal energy is lower, if the temperature is lower than h cut omega, if the value of kT is less than h cut omega, if T is smaller than h cut omega by K, and you pump in a very, very small amount of energy to the system. Let's say the system is hanging here in the ground state, in this state over here. Unless and until you give the system an energy that is at least h cut omega, there is nowhere for it to go over here, right? You cannot give it energy equal to h cut omega by 2 and expect that the system will get excited. In order for the system to get excited, you must give it a minimum quantum of energy, and that quantum is h cut omega. Anything smaller than that, the system will be like, I don't know, what do you want to do? What you want me to do with this? I don't know what to do. This is like currency, right? If I gave you 1 penny, maybe you can do something with that penny. But if I gave you half a penny, you can't do anything with half a penny, right? Of course, even with 1 penny, you cannot do anything. These days, the quantum is probably, I guess it's 5 cents, right? 5 cents is the real amount that you need to do something. But you could do even with 1 penny. Sometimes things are priced with 99 cents or something like that, right? But the concept of half a penny does not mean anything. So that's what happens in quantum mechanics. You have these discrete energy levels. And this is why if the temperature is too small and you pump some energy into the system, there is no capacity for it. So strictly speaking, it's a differential. It's a 0 by 0 type of situation. And now we will show mathematically as to how, when you use this quantum mechanical picture for the harmonic oscillator, you get the right heat capacity behavior across all temperatures. Okay, so that's what we are going to do next. So physically, our picture, in a sense, it's similar to what we had earlier. So we still have every atom in my system. I am still assuming that we have n independent atoms, okay, moving independently in 3 directions. X, Y, Z. So this is the same as the classical case. So I have every atom here can move along X, can move along, I have to be careful, yeah. So move along Y and move along Z, right? In the classical case, what we said was classical mechanics, we said U is equal to U naught plus alpha by 2, X square plus Y square plus Z square. Now, and then we added a kinetic energy and we said E is equal to U naught plus alpha by 2, X square plus Y square plus Z square plus 1 by 2m px square plus py square plus pz square. This was the classical mechanics picture. In quantum mechanics, this total energy will be replaced by something that looks like, so we still have, so what did we have here? So here we had n independent oscillators moving in three directions, right? So effectively you had 3n independent oscillators. So same in quantum mechanics, you're going to have 3n independent oscillators. Now we do not think about their potential energy and their kinetic energy separately. We lump it together and we say that each of these oscillators could be moving with a frequency. This frequency could be omega 1 for the first oscillator. It might be omega 2 for the second oscillator. It might be omega 3n for the second 3nth oscillator. Okay, so these are variables which are denoting the frequency with which every oscillator is moving. In classical mechanics, what is the frequency? The frequency is connected to, related to alpha, right? Frequency tells you how stiffly are you increasing around the minimum. So we have a similar frequency term over here. So, and so this is where, if you haven't taken quantum mechanics, this is going to be very abstract. And that's why I posted material after today's class. Please go back and look at it. I know we are meeting again tomorrow morning, so there is not a lot of time, but please try to look at it. Otherwise, tomorrow's class will be more confusing if you have not taken quantum mechanics or if you didn't like quantum mechanics. So every oscillator is moving with a certain frequency that changes. So in a classical mechanics picture, this would be equivalent to saying that the alpha for every oscillator is different, right? We could just say that it is classical. It is still following the nice smooth harmonic well. It's just that the value of alpha can be different. So we are saying something similar, but now on top of that, we are going to use a different value for the energy. So given a certain frequency, omega alpha, the energy values that are allowed look like E alpha is equal to U naught plus half plus N alpha multiplied by H cut omega alpha. Where did this equation come from? Well, that is the solution to the energy eigenvalues of the quantum harmonic oscillator. So this is energy eigenvalues of a quantum harmonic oscillator. I'm not going to derive this here. That's why I posted the Wikipedia article. There are two ways to derive it. One is to do it using Hermite polynomials. You actually assume the form of the wave function and do it. The way I really like a lot is known as ladder operators, which is creation and annihilation operators, which is one of the most beautiful things in physics. So what does it mean? Let me give you an intuitive sense for this. So I will write down this equation on the next page, and this is equation number 12. So equation number 12 says that given frequency alpha, if you knew that a certain atom was moving with a frequency omega alpha, the energies that it can take are going to be given by E alpha is equal to U naught plus half plus N alpha H cut omega alpha where n alpha can be 0, 1, 2, something like this. Okay. So what does it mean physically? Physically or geometrically, what it means is actually, I will just draw one curve and I will draw straight lines. So you have these energy and that's going to look, this is the ground state energy, and I'm plotting it as a 0 here. So this corresponds to n is equal to 0. So for a certain frequency, let's take a 2-minute break, okay? I'm gonna take a 2-minute break, and then I want to do maybe 20 more minutes. So let's take, yeah, a 2 minutes break and then come back, not longer.
Quick question. Why do we have a
Go ahead.
Why do we have a U naught term in the energy eigenvalue? Shouldn't it just be n alpha plus half ℏ omega alpha?
Yeah, so the U naught comes from the vibration, from the stability of the crystal.
Okay, but like we seem to be like adding it additionally. Like if we're just assuming a quantum harmonic oscillator,
Sure, but
I
we
mean-
are talking about quantum harmonic oscillator that is making a crystal. So we are taking into account that the crystal exists. You can ignore it. If you don't like U naught, you can ignore it. It's just a
Okay,
reference.
alright.
The thing to keep about
Okay.
energy is it's only true up to reference. But give it 2 minutes, then we'll start again.
Okay.
So 6:53 will start at 6:56. Okay, so I'm going to plot the, now it's recording, right? Yeah, is it? Yeah, recording, good.
It is.
So I'm going to plot the energy eigenvalues for the quantum system now, same thing versus X. So now you will have a ground state. And the point Vedant was asking earlier is, why do I have a U naught? So I'm basically saying the ground state has some U naught. So if I set U naught is equal to 0, that would correspond to here. So if this U naught term bothers you, don't worry about it. All I'm saying is that the ground state for the whole thing is lifted by a certain value, which corresponds to the stability of the crystal. So U naught is some negative number actually, but I won't let this not be a bother. It just drops off everywhere. So now this is your ground state. Your next state is not going to be any continuum like this, like you did for the classical harmonic case. No, that's not allowed. Your ground state will be up here at a level. The first excited state is going to be, so this is ground state. So the ground state is actually U naught plus h cut omega by 2. So, and this we are talking about oscillator with frequency omega alpha. So the ground state is h cut omega alpha by 2. The next one in this case is, we have to add 1 to this thing, right? So the energy of the next one is going to look like 3h cut omega alpha by 2. The energy of the next, the second, so that's the first excited state. The energy of the second excited state is going to be 5h cut omega alpha by 2. So all of a sudden the parabola has disappeared, but it still matters. And that is really the classical connection. Now you have to think about the wave functions. So in the first excited state, the wave function, in the ground state, the wave function is going to look like this. As you go higher, the wave function will start to show nodes, and it will look like this, and there will be more nodes, and you can connect something like this and again get the same parabola type of picture. But I don't want to worry too much about the form of the wave functions of the quantum harmonic oscillator. We are not going to use them. But I want to make a point here is that the energy in this case, the E alpha starts with U naught plus h cut omega alpha by 2 when n alpha is equal to 0, U naught plus 3 h cut omega alpha by 2 when n alpha is equal to 1, U naught plus 5 h cut omega alpha by 2 when n alpha is equal to 2, so on and so forth. Okay. And this is true for any given alpha. We don't know what is the frequency. What is the possible value of omega alpha? We don't know yet that. How does that affect the picture? What it does is that if you have, depending on whether you have a smaller omega alpha or a larger omega alpha, the wave functions will be broader or they will be tighter. Okay, so the curvature of this envelope that I drew over here will change depending on the value of omega alpha. But again, don't worry about the wave functions. Keep this one in mind. Okay, so we are ready to go to the think about this and start to connect to the partition function. I'll write down formula 12 again on the next page, because this is a bit different from how many of us normally think about. So for any omega alpha, we have E alpha corresponding to that frequency as U naught, which is the crystal energy, the stability. U naught is what makes our crystals stay together. So again, to answer your question, Vedant, if U naught was not negative, the atoms would have flown away from each other, far off somewhere else. So it's just a scale. So this is going to be U naught plus half N alpha H cut omega alpha. And N alpha here is called occupation number of oscillator omega alpha. Well, we talked about occupation number last time, right? So this is an occupation number of oscillator omega alpha. What happened to sometimes my screen disappears. One moment. Okay, there it is. And now comes the concept of phonon. N alpha is also known as the number of phonons. So what is a phonon? A phonon denotes quantization of the vibration energy of a crystal. So in omega alpha, if in the frequency omega alpha, the system was in ground state and N alpha was equal to 0. So if for frequency omega alpha, and really, I'm not here to teach you about phonons. That is the concept of solid state physics. I can just give you a brief summary of what phonons are. If for frequency alpha, system was in ground state, then N alpha will be 0. And we will say 0 phonons of frequency omega alpha. If N alpha is equal to 1, we would say 1 phonon of frequency alpha. Omega alpha, and N alpha can be infinite. If N alpha is infinite, we would have infinite phonons. And that's why phonons are bosons. Phonons are bosons. There is no restriction on their occupation number. They can go from anywhere from 0 to infinity. One point I want to make here, which used to confuse me as a grad student, that phonons can exist in classical mechanics also. Here I showed you phonons by introducing quantum mechanics. Phonons can also exist in quantum mechanics, and you can go and look up Wikipedia on it, and it really corresponds to stationary waves and things like that. You can read about it, but we are not going to get into that. Okay, so this is the idea here, that every omega alpha corresponds to a certain type of phonon. Every frequency corresponds to a certain type of phonon. And depending on the occupation number, you say, how many phonons do you have of that frequency? So let's look at the big picture here. What do we have? We have atom number 1, atom number 2, going up to atom number 3n. This one is oscillating with a frequency omega 1. This one is oscillating with a frequency omega 2. This one is oscillating with the frequency omega 3n. On top of that, I'm saying that even if you had omega 1, you could be in the ground state, you could be in the excited state 1, you could be in excited state 2, so on and so forth. Same one here. For omega 3n, you could be in ground state, you could be in excited state 1, you could be in excited state 2, so on and so forth. So it's fairly more complicated than the way we think about classical life. But now I can write down the energy of a microstate and then really get back to statistical mechanics. So what is the energy of a microstate? The energy of a microstate in this case will be given by going to every frequencies, going to every atom and seeing what is the energy, going to every atom, going to every single direction for that atom, right? So we have 3n independent harmonic oscillators. We go to every harmonic oscillator and we look at the energy of that harmonic oscillator, right? And they are independent, so I can sum it up. So which equation number did we get to equation number 12? So use 12 above. So what do we get? We get E nu is equal to alpha is equal to 1 to 3n. And then E alpha, what is E alpha? E alpha is equal to U naught half plus N alpha multiplied by H cut omega alpha. So this is the energy of the of a given microstate. And a microstate, once again, is characterized by the value of the occupation numbers. So this is the picture that I mentioned last time in class. So this is equation 13. And this can be written as summation alpha is equal to 1 to 3n n alpha h cut omega alpha plus summation half multiplied by this summation alpha is equal to 1 to 3n h cut omega alpha, and we will make Vedant happy now and set u naught equal to 0. If you want to keep u naught non-zero, you can keep it. It will just remove. It will not show up in the expressions that we are going to derive next. Okay, it will just differentiate out. So this is for pure laziness. There is no other reason. Okay. I showed you that you can keep it if you want. Maybe it is useful for something. You can work with it. But for now, we are just going to set u naught is equal to 0. So this is E nu is equal to this thing. I'm going to stop in 5 minutes. Okay, I won't push it further, and then we will start tomorrow in class. So I have the microstate energy, and now I want to connect to thermodynamics. In order to connect to thermodynamics, I of course need my partition function, which is going to depend on beta, n, and v, the canonical partition function. And what's that going to be? That's going to be summing over all microstates and doing e to the power minus beta E nu, right? And now I have the formula for e to the power minus beta E nu. So I will have every microstate e to the power minus beta and a summation up here that goes from alpha is equal to, you can see why I removed the u naught, because it's like summation in the power of a summation, you know, it's kind of messy. But you have seen something like this earlier, so hopefully you will recognize it. This will be n alpha plus half multiplied by h cut omega alpha, right? And instead of talking about nu, I can now talk about n alpha. Every n alpha can go from 0 to infinity. So in tomorrow's class, we are going to deal with this super complicated looking partition function where you have summation of an exponential, and in the power of the exponential, you have another summation. So, and this is where I'm going to stop. I just want to mention you, where does Chandler talk about it? Chandler does all of this. All of today's class is 1.5 pages of Chandler. He really skims through it. All this just, you cannot see virtual background, but that's fine. So Chandler section 4.3, phonon gas or fluctuations of atomic positions, goes over 14 pages that I wrote right now in 1.5 page. Please go and read it. It's quick to read because it's only 1.5 page. And given the details that I went through, it will make sense to you. So what we have done today is we have stopped before Chandler equation 4.3, exercise 4.3. And that's what we are going to derive tomorrow. And we will start, I'm not going to do a recap tomorrow, okay? So please, please, please go through Chandler section 4.3 before tomorrow's class. It's only 1.5 page. It will not take time, okay? And please go through it. It should make sense given what we have done. And then we will compute this summation tomorrow. And just like in StatMech, summations look complicated, but if you have independent summation, if you have independent quantities, they really become very simple. So this complicated looking sum will become a product of very, very simple sums. And we are going to calculate it, and then we will get going. Any questions about this? Okay, if not, see you in 16 hours tomorrow morning in class. Bye-bye. Have a nice evening.